This mirror focuses solar radiation in this device, which is usually called the term receiver. We see that the mirror is fixed to the wall, and therefore it cannot move, and this fact is its difference from these widely known devices, which must constantly move from morning to evening, according to the movement of the sun across the sky. This is my solar station, but it does not move from morning to evening. However, I have to do this change in the vertical angle of its mirrors about once a week. We see that this receiver is fixed to the mirrors, but here I fixed it to the ground. This type of solar heaters also requires a change in the vertical inclination of the mirrors, but approximately 10 times a year, and it was described by one of my old videos. But now my mirror is completely motionless and I will never change its position, and the topic of this video is a description of the features of this type of solar heaters. Obviously, this type of solar heaters is interesting for these cases when we plan to cover the south wall of a house or building with reflective sheets. Or we plan to use reflective sheets to cover the outer surface of our southern fence or the inner surface of our northern fence. Interestingly, reflective sheets can be very cheap, and for example, these sheets of stainless steel of this mark have a price of $12 per square meter. We understand that solar energy from our reflective sheets can heat air or water for space heating of a house or building. Interestingly, the same reflective sheets are now used in this system, which produces hot water for my summer cottage. This is a similar solar heater, but here I use not expensive steel sheets, but a cheap reflective polymer film, which helps heat these 50 liters of water to a temperature of 89 degrees Celsius. This idea may be interesting for cases like this solar cooling system, where these 5000 square meters of solar collectors produce a lot of heat with a temperature of about 90 degrees. The heat goes to the inlet of this absorption chiller, which turns the heat energy into cold that is used to cool a large school instead of traditional air conditioners. This system cost $10 million, but I plan to drastically reduce the cost of such solar cooling system using similar solar heaters, and maybe my third YouTube channel will describe these ideas in a few months. It is obvious that our immobile mirrors can not only cover houses or fences, but also they can form similar long rows for producing a lot of cheap heat. These two versions may differ significantly, and this is the example of the summer version. This is another example of the summer version, but let's look at the features of similar winter versions, which may be interesting for space heating, for heating pool water, or for other purposes. Let's watch how the spot of solar radiation from my mirrors will move from morning to evening during one day. It is morning and the spot is here, and these are time points during one day of the 17th of October. Now the sun is exactly opposite the mirrors, and at the same time this is the moment when the spot is located in the lowest position. So, we understand that our receiver should be located here if we want this spot of solar radiation to be inside the receiver during 6 or 8 hours. It was a situation where the mirrors and receiver are located exactly along this west-east line, but we understand that our real reflective walls or fences may have a different direction. That is why, let's look at the similar experiment when I temporarily fixed the western edge of my mirror not on this stake, but on this. Therefore now the west-east line is located here, and this angle is 5 degrees, and now we will see the movement of the spot of solar radiation from the mirrors during one day of the 19th of October. This is the moment when the sun is exactly opposite the mirrors. So, we can conclude that 5 degrees deviation from the west-east line is not a big problem. But let's increase the deviation angle to 15 degrees, and my next experiment is based on the fact that I temporarily fixed the eastern edge of my mirror not on this stake, but on this. That is why now the west-east line is located here, and this angle is 15 degrees. It is morning of the 29th of October, and we can observe the movement of the spot of solar radiation at different points in time from morning to evening. This is the moment when the sun is exactly opposite the mirrors. We can notice that increasing the deviation angle will reduce heat production by our receiver. I think that the deviation angle must not exceed 15, 20 or 25 degrees. If the angle is greater, losses of the heat production during a day can reach several tenths of %. One of my old videos showed this experiment, and we must pay attention to the position of this spot at noon of the 5th of November. Of course, the height of the sun above the horizon will decrease in November and December, and therefore we see that the spot position rises day after day. I remind you that these are positions at noon on different days. This is the highest position of the spot, because now is almost the winter solstice. After the solstice, the spot will gradually lower, because the height of the sun above the horizon begins to increase. This is the spot position in early February, and we saw that the spot was inside the white screen during 3 months, from early November to early February. In addition, this period may not be 3 months, but 4 or 5 months, if we increase this screen height or decrease this distance between the mirror and the screen. Thus, a high receiver can produce heat during 3, 4 or 5 months around the winter solstice. But if we need a long operating season for our solar heaters, we have to change the height of the receiver location, as I am showing you now. This is the first opportunity to extend the operating season for our heaters, and I will show the second opportunity in about a minute. After the season ends, we can use a similar summer receiver. Also, it is obvious that our mirrors must have a different radius of curvature, so that the spot of the radiation focuses exactly in this summer receiver. But we must pay attention to this receiver shadow, which can slightly reduce our heat production if it covers the lower part of the mirror. This shadow is important around the winter solstice, and we see that the higher the sun above the horizon, the situation is better. In addition, increasing the focal length of our mirrors solves the problem of the shadow, like this situation where we see this shadow in the winter solstice. Now I show the second method of increasing the operating season of our solar heaters, when we have to change the distance between the receiver and the mirror several times a year. But we must understand that if the receiver should have this position in December, the mirrors should focus the solar radiation at about this place. We understand that the height of the sun in February or October will be higher, and therefore the position of the receiver will be different. Unfortunately, the April position of the receiver can lead to the fact that the solar radiation will focus poorly, and therefore its efficiency in April will be poor. Let's take a look at this rose bush, which has been illuminated by solar radiation from my mirrors for several weeks, and we see burns on the leaves of the bush. In addition, the radiation from our mirrors can destroy grass, especially if the focus of the radiation coincides with the ground surface. I remind you that the winter version of our solar heaters should be operated around the winter solstice. In contrast, our summer version works well during several months around the summer solstice in June. Between the winter and summer solstices, the midday position of the spot from my mirrors moves very quickly, and now we see the movement of the midday position day after day. But moving the midday position becomes slow in April and especially in May. That is why our heaters get the opportunity to work well during 5 or 7 months around the summer solstice. But it is obvious that the mirror must have a different radius of curvature, and for example these mirrors focus solar radiation on the surface of the receiver. Of course, I did not describe all the differences between the winter and summer versions, and for example the summer version uses different type of receivers, and increasing the width of the receiver allows us to operate the summer version during 5 or 7 months without changing the position of the mirrors or receiver. Unfortunately, I have yet not well studied the summer version, but I plan to research it in the coming months, and maybe I will describe the summer version in more detail in my future videos.